The beginning part of 7.2 looks very familiar to what we've talked about before because it is our introduction to what's called the indefinite integral. And doesn't that just look like the integral that we saw before? Okay. The difference is we don't have an A and a B. They aren't telling us what interval to look at this on. And so what we're finding with our indefinite integral is just what it has at the top, the family of the antiderivative function. So all of the functions whose derivative will end up being that little f of x. Those functions all differ by just a constant c. The difference between this and the definite integral was finding the area under that curve on some given interval. This is not. This is just finding the function that is the antiderivative of the one inside the integral. So very similar. When we evaluate the indefinite integral, it is just finding a function. As you can see in that second part up there, if capital F is any function such that the derivative of capital F equals little f of x, then the integral of little f of x dx is going to equal capital F of x plus c. And c just represents any constant that would be tacked on the end of that. A definite integral, our answer at the end is some value. An indefinite integral, our answer at the end is some function. However, our rules involving those are going to be very, very similar as we go. So as we look at this, our answer at the end of these problems is going to be some other function whose derivative is what you see inside the integral. The first one, pretty straightforward, pretty easy. You just have to be careful when you're thinking about like those trig derivatives. The second one's a little bit more challenging, and we're going to talk about two different ways we could attack that particular one. Kind of easing our way into it, that very first one, the integral of x squared minus sine x dx. We can look at each of those individually. The integral of x squared, thinking about its antiderivative, think backwards through your power rule, right? So I have some function, capital F of x, that when I take the derivative of this term, I end up at x squared, right? So thinking backwards, I would have started with power rule, something one bigger than that x squared. So that when I subtract 1 from the exponent, I get a 2. Part of my power rule says we take that exponent times the number in front of x, and we end up with 1. So 3 times what gives me 1? 1/3, right? So this first term would have been a 1/3 x to the third, or x cubed over 3. And then it's always a little, you got to slow down and think about sine and cosine. Obviously, we know that they are derivatives, antiderivatives of each other. It's just the whole positive versus negative thing, right? So I would have taken the derivative of cosine to get sine. It's this negative that I'm wondering about. Okay, do I put a negative here or do I put a positive here? Well, what is the derivative of cosine? Negative sine, which is here, which means this is positive. And then this represents a function, but all functions would be with that plus c on the end, because it is those two terms plus any constant. It doesn't matter what the constant is. When I take the derivative of this capital F, we get back to the x squared minus sine x. Any questions on that? Okay, the second one, there's kind of two different ways to attack this one. I think one is significantly easier than the other, but we probably need to address each one of those. What's one of the things that stood out to you as we look at that first, or that second example? What one thing that we would have to like think through as we anti-differentiate that? Are we looking at like power rule, product rule, quotient rule? What kind of rule are we looking at up there? A chain rule? Okay, agreed. We can look at that as a chain rule problem. Now, thinking backwards through chain rule, I think, is one of the more challenging things as you think about the antiderivative of this. So let's think backwards through our chain rule. In chain rule, you take the derivative of the outside function. So let's just focus on the outside function. When we took the derivative of the outer function, our outer function would be like this x squared, right? Taking the derivative of that, it would have started at an x cubed, yes? And we would have taken 3 times something and ended up at a 1, which means sitting out front, what it needs to be a 1/3. The inside would not have changed on the first step of that power rule, right? Now, if I leave it like that, I'm sorry, I said power rule, chain rule. If I leave it like that, when we did our derivative, let's look back at this. If we did our derivative here, I would have multiplied 3 by 1/3 and gotten 1, subtracted 1, and gotten 3x plus 1 squared times the derivative of the inside, right? And the derivative of the inside is 3. But we don't have a 3 outside of our answer. So how do we fix that? I can't have a 3 outside my answer because there isn't one up here, which means as I multiply by the derivative of the inside, we would have had to have what else sitting outside of our function? Okay, let's look at this one more time. Taking the derivative of this guy right here, I would have taken the 3 times the 1/3, right? And that would give me 1. Subtract 1, we'd get to 3x plus 1. Times the derivative of the inside would have gotten me to 3 times 3x plus 1 squared. Comparing that to what's up here, there isn't a 3 right here, is there? So that means that when I did times the derivative of the inside, what was sitting out here would have made it a 1, which means we need another 1/3 sitting out here. Okay, that's where chain rule gets really tough. So ultimately this would be 1/9 3x plus 1 cubed plus any constant. Okay. Now, I said there's more than one way to think about that. We just thought backwards through chain rule. Tough, because you have to take into account the exponent on the outside, but we also have to take into account what we get when we do the derivative of the inside, right? Did anyone see another option of how you could have attacked this? Algebra can make this problem way easier. What does it mean to do 3x plus 1 squared? Foil, right? What if we had just foiled our integral instead? Okay, well, 3x plus 1 times 3x plus 1, isn't that, let's see, what, 9x squared plus 6x plus 1? Does that look easier to anti-differentiate? Because now I just get to do power rule on each of those terms, don't I? Okay, so thinking backwards to a power rule on each of those terms, this would have come from an x cubed. 3 times something gives me 9, which would be 3. Okay, this one would have come from an x squared. 2 times something gives me 6, so that would have been a 3. And this would have been a, 1x plus c. Okay, those look like very different answers, don't they? So how are they the same? Well, if I were to write this 3 times, and foil and foil and foil, my biggest term would have been a 27x cubed times 1/9 is 3x cubed. Okay, so they are the same thing. So sometimes algebra can make this a lot easier, and that would have been to foil and use product rule on that one. Look for things like that to help you. Okay. Rules like we see up here, rules for our indefinite integral, those are the same rules that we've already seen for a definite integral. So those things are not changing. The first one is talking about a constant multiplier. If we have some constant times our function, we can slide that constant out front and just look at the integral of the function. Very basic example of what that's talking about, the integral of something like 5x dx. Well, 5 is a constant, which means I can slide it in front of the integral and just do the integral of x dx. Sometimes sliding that constant out of there, especially in something like a power rule, can make it easier to take the antiderivative. If we are taking the integral of two functions that are being added or subtracted, this is not what's happening, but it kind of looks like that integral is being distributed to each of those functions. I can do the integral of one function, keep the sign between them, integral of the second function. That is probably how you thought through this one right here without knowing that we were basically breaking it and doing the integral of each one separately, right? Okay, the power formulas. They are formulas. Guys, this is what we think through every time we do thinking backwards through our power rule of derivatives. This is saying that some function to a number, some x squared. Okay, so this would be like an x squared equals, and then the antiderivative of that would be to add 1 to the exponent and put a multiplier out front of 1 over that number. Very similar to what we just saw. If I was doing the integral of x squared dx, that equals, and what this is saying is add 1 to the exponent, so from 2 go up to 3, but that you need to then multiply the front of it by 1 over that number. We've already talked about that a lot, about thinking backwards through our power rule. That's all that's saying. And then your last one is, okay, then that weird case, so what if the exponent's a negative 1? That's when it is 1 over x, and the antiderivative of 1 over x is natural log. We've also talked about, notice that they put that x, or that function, into absolute value symbols right there because of the domain restrictions on a natural log. X would have had to have been some positive number for the natural log function to have existed. So we take that into account as we anti-differentiate 1 over x. And with everything on our indefinite integrals plus c. Any questions on any of those rules? Okay, now these look like a ton of new rules. I'm not even really sure that we need to write these down. Can you guys see your trig derivatives up there? As long as you know your trig derivatives. Now, here's the tricky part, thinking through the positive negative part of it. So, for example, on something like cosine being our antiderivative, if it's a positive sign in here, well, the derivative of cosine is negative sine, which means this would have had to be a negative cosine. And we are, again, that's something we already talked about today. So just make sure that you are remembering your trig derivatives and paying close attention to the sign as we flip back and forth or take the integral of a trig derivative. Think through your sign carefully on that. Okay. These ones, again, ones we probably know. However, if the base of our exponent is something other than e, I think we forget the whole natural log of the base thing, so that's probably a good one to have down. But just a reminder that e to the x, its derivative is e to the x, which means the integral of e to the x is e to the x. If that base becomes something other than e, we have to take into the account that when we do like 3 to the x as derivative, we get 3 to the x times the natural log of 3, which is why to get rid of that times natural log of 3, we have 1 over natural log of the base. So again, thinking backwards through those derivatives, these formulas can kind of help you with that. The next couple, we definitely want to have in our notes because they are not ones that are easy to think backwards through. And in fact, if you would like a proof of them or a step-by-step of how they are developed, you can look in your book, but it's not worth it. Just have this in your notes that if we have like the natural log of x in our integral, so the integral of the natural log of x dx, that the antiderivative of that would be x times the natural log of x minus x plus some constant. And if the base is something other than e, we'd be looking at that second one. All right, anyone still need this page? Okay, this example is in here for a very small part and not something we focus a lot on, but I just want to point out the directions. There are two very important pieces to the direction, and it says verify, which means a lot to us. Verify the identity, and then it says by differentiation. First of all, when it says verify, they are telling us the problem and the answer. What we are tasked with is showing that that's true, okay? So there is no like work to be done as far as figuring out what the integral of e to the 3x dx is. It's this, it's 1/3 e to the 3x plus c. What we have to do is show our step by step that they actually are equal to each other. And then the second part of the directions tells us how we're going to do that, by differentiation. So what it's saying is we're going to differentiate both sides, or take the derivative of both sides and show that the derivative of those two functions are equal, which means they would be equivalent functions. The verify part of it goes back to geometry proofs, right? We don't get to skip steps because otherwise it'd be like, yep, true, trust me, move on, right? We don't get to do that. We actually have to show our work. So let's talk about how to show our work on something like this. It says by differentiation, which means we're taking the derivative of both sides. So show taking the derivative of both sides using your derivative notation. The derivative of this side would equal the derivative of the right-hand side. That's one step, is just showing that I'm taking the derivative of both sides. The left-hand side is very easy to clean up because the derivative and the integral essentially become inverse functions of each other. When I take the derivative of the integral, we get the interior function, e to the 3x. Okay. As we look at the next one, it looks like we can do the derivative of each of those terms individually because it is separated by an addition. So let's start with our 1/3 e to the 3x. 1/3 is just a constant multiplier times the derivative of e to the 3x, which would be e to the 3x times the derivative of the inside, which is 3. And then this is also something we got to make sure that we show. What is the derivative of c? 0, right? It's any constant. We don't know what constant it is, but it doesn't matter because the derivative of the constant is 0. And I'm going to show that I have taken the derivative of that constant by putting plus 0 there. Because we're showing our work, right? Normally I wouldn't say write plus 0, but I'm showing all of my steps to verify. And then 1/3 times 3 is just 1. And I get to that e to the 3x equals e to the 3x verified. Both sides end up equivalent. Not a ton of work. Start by showing you're differentiating both sides, like one step of work, and that they end up at the same thing. All right. The last part today is going to be our intro into U substitution. Like I said, today we're going to do U substitution, integrating by U substitution with training wheels. And I'll tell you what our training wheels are. They're going to give us something like this. Find the integral of sine of x e to the cosine x dx. Today, you're going to get this other little piece of information. Let U equal cosine of x. That's your training wheel. It's going to tell us what we're going to let u equal today. Your job as you're doing this is I want you to pay attention to kind of how they're picking their u. Tomorrow we're going to remove that training wheel. I'm not going to tell you what u is going to represent. Eventually we're going to have to pick that function. And what do I mean by that function? If we look up at that integral, we have basically three different functions that you could pick. We have a sine of x, we have an e to the cosine x, or we have just plain cosine x if I were to look at that exponent. And they're saying use cosine x, okay? Your steps will not change. So that's why I have it up here so that we can kind of have that in our notes and give you like a roadmap of how you're going to attack these problems. And then we'll use this example in the next one to kind of show what those steps mean you're actually doing. Okay, so using our steps for u substitution. Step number 1, sub u into the equation. So as I look over here, it says u equals the cosine of x. So I come over to my original equation and I find where that function is. Cosine of x is located right there. I'm going to replace that with the letter u. I'm letting u hold the place for cosine of x. So my equation now is going to look like sine of x e to the u dx. Step 2, find du dx and solve for dx. That is coming over here. You're going to differentiate both sides. So we have u equals cosine of x. If I take the derivative of both sides of that equation, it becomes du dx equals derivative of cosine, negative sine of x. Okay, that's the first part. Find du dx. Du dx equals. Done. Second part, solve for dx. Dx is currently in the denominator here. I want to use my algebra to get that by itself. Yeah, it's going to look like it kind of flips. The long route is I would multiply by dx first, and then divide by negative sine x. What it kind of looks like is that those two terms just flip-flop spots every time. It's going to look like that, okay? Step 3, come over here and replace dx with what it equals. Dx equals du over negative sine x. Here's dx. And instead of dx, I'm going to replace it with du over negative sine x. Now, the entire point of this, and we'll talk a lot more about this tomorrow, is doing that substitution should do something to help me. And in this case, that is going to simplify out a sine x in this problem, getting us down to one variable. I have a sine x in the denominator, I have a sine x in the numerator, and those would cancel. Leaving me with, it would be careful, don't lose this sign, or this negative, the sign on the sign. That negative I can slide out front of my integral, e to the u du. Four, anti-differentiate and clean it up. Anti-differentiate, the negative is just going to be tacked on our antiderivative. But what is the antiderivative of e to the u? E to the u, right? That's one of our e to the x's. That one's kind of a weird one because it doesn't look like it changes. But we did anti-differentiate e to the u is e to the u. And the last part is I can't leave it as u. I'm going to put back in what u actually equaled, which is cosine x. Negative e to the cosine x plus c. Now, this works. This one actually was a chain rule one. You could have thought backwards through chain rule. It would have worked. It also works to use u substitution on this. Eventually, we're going to get to the point where it's going to be problems that we will want u substitution, and we can't think backwards through them. Questions? Okay, let's try one more here. This is definitely one that I probably would want to think backwards through. Given the integral of x squared, square root of 5 plus 2x cubed dx, let u equal 5 plus 2x cubed. Ready to take?
Okay, yeah, definitely need to practice ones that will land on.
Okay, let's follow our steps here. Job 1, insert in u, which would be for this entire function inside our radical. Go over to u and take the derivative of both sides. Okay, well, the derivative of 5 plus 2x cubed is going to be 6x squared. Derivative 5, 0, right? And solve for dx. Come back over here and replace dx with du over 6x squared. Okay, and do we see why this one is going to be helpful for us again? Usually at this point looking for something to simplify out of there. I have an x squared in the bottom and the top. I can get rid of those. What constant would I be sliding out in front of my integral on this? 1/6, right? The 6 in the bottom is actually the fraction 1/6. I'm going to elect to write the square root of u as u raised to the 1/2 because I think better through the antiderivative of the square root of u as in power rule there. So again, thinking power rule. Okay, u to the 1/2, thinking backwards through that would have been add 1, right? And then 3/2 times something gave me a 1. What's that something need to be? 2/3, right? 3/2 times 2/3 is 1. So then that tells me what fraction's actually sitting in front of the u, which would be what, 2 over 18 or 1/9? Are we all okay with that? And then sub back in for u. U being 5 plus 2x cubed. Way easier way of thinking backwards through a chain rule, especially with that like power function outside. Okay? Any questions on that? Okay, so with that being said, try this last one. Matches the one we did at the beginning, which we did in 2 different ways, right? Try it using u substitution and see how that goes. Correct. Correct. All right, let's see how we did. Replace 3x plus 1 with u, so it just ends up being u squared. Take our derivative. Okay, well, the derivative of 3x plus 1 is just 3. Solve for dx. Would be du over 3. And this one's a little different because nothing simplifies. But what we're looking at is a little bit easier to think backwards through our power rule than the chain rule version of it, right? So I can still slide that 1/3 out front. And now think backwards through my power rule here. It would have been a u cubed. 3 times something gives me 1. That something would be a 3, 1/3.
1/3 times 1/3 is 1/9. And replace u. Which is the first version of our answer that we got, right? So this is just giving us a third option of how to find our antiderivative of something like 3x plus 1 squared. I know that it looks like a lot of work. I feel like you'll be able to simplify it a little bit, and it's giving us an option of functions that are not something we can think backwards through or are kind of ugly, like a chain rule type of problem. Okay. Your assignment tonight out of the book, like I said, tonight, training wheels. You get u, but you guys got to try these problems. Tomorrow, I remove the training wheels, and we have to go start picking our own function u, and how do we pick that out of all the options in our problem.